Welcome back, everyone. If you can take a seat, we're going to resume. Okay, so the next session is titled Focus on AIs for Agents Embedded in the Real World, Open-Ended Environments. And we're going to have two talks. The first one is titled Planning and Acting to Learn. And we will have three speakers for this talk. First one will be Luciano Serafini. So Luciano, please.
Okay, good morning to everybody. I am Luciano Serafini, the head of the Data and Knowledge Management Research Unit. I will briefly introduce... C'è il microfono. Questo? Pronto? No. Però io preferirei perché così... Parlo forte, va bene così. Okay.
No, perché c'è lo streaming.
Ah, c'è lo streaming, sì. Okay. I will shortly introduce the other two speakers, Leonardo Laman, Tommaso Campari and Leonardo Lamanna, who actually did the real work. Okay, so I will do the introduction. The moment, I have to understand how it works. Okay. So we are interested in building agents that are capable to operate in an unknown environment. So the environment is unknown a priori. And they should be able to plan, act, and act in order to learn a model of the environment and use this model to solve a set of unforeseen tasks. So there are two things, important things that I want to notice here. So we are planning and acting to learn. We are not learning for planning and acting, but our objective is learning. So our task is an epistemological task, so we want to learn something. And to learn it, and we don't know the task beforehand. We don't know what the agent should do after this learning. Okay? And then the the model should store the learned model of the environment in some memory. Okay? And this memory should be kind of permanent. So the agent should not forget what it has learned. And the third point is that the agent should also reuse common sense logic, should be ready to use standard common sense logic, common sense knowledge, sorry, that is typically available in large language model or large foundational model. Okay, so the agent do not start from scratch, so it has all this bunch of knowledge, but we know that we have to notice that this is not enough because there is no large language model that know exactly the configuration of this room. So from the language model, you can understand what are a chair, what are a people, what are speakers, what are a microphone, but how this specific room and this specific moment is configured, there is no large language model that contains this knowledge. So that part of knowledge should be learned. Okay, so we have to plan. And how can we plan? Oh, there are many, many possibilities to do planning, depending on the model that you have. But in these two presentations, for example, we will do planning with two very, very heterogeneous methods, but still they are planning. So the first method is based on partially observable POMDP, okay, POMDP. And the second one is based by using background general background knowledge, asking a GPT or a large language model to provide a general plan for executing actions. So this is the planning. So what about learning? So what do we want to learn? Okay, we want to learn, like in this, in the left part, we want to learn a POMDP that represent the domain, the objects that are present in the environment, and the dynamics of the environments. In the other case, where we use the large language model for doing planning, we want to learn the configuration of the environment. For example, a map, a semantic map, where are the objects in that specific environment? So we want to ground. The problem is that model is not enough. We need to ground a model into our specific situation. So this is the learning part. And what about acting? Well, it is not enough to learn. We have to learn and to plan. We want to act and to execute what we plan in order to achieve the tasks. And in particular, sorry, the important thing is that while we are executing, so we first, well, in the work that I presented, we suppose that the agent is equipped with a set of primitive actions that is capable to execute, okay? And the model will be somehow described also in terms of these actions. And the agent obtained observations after executing this action, as in the usual POMDP setting. So it obtained observation, and what can be done with this observation? Well, it can use in two ways. The first way is to improve the model, so to increase the knowledge about the world. Okay, and the second method is to, if he is trying to accomplishing some task, he can check if the task is finished or not, or how much is it advanced. Okay, so these two ways of using observations are not separated. They can be done at the same way, at the same moment. Okay. And so this means that we want to build agents that while they are accomplishing some task, they also learn, okay? So the knowledge is keep on increasing. Okay, so around this topic we are already working since a while, and here is a list of publications. I don't need to read it, okay? Well, these are journals and conferences. Today we have Tommaso and Leonardo that present our two recent work, which are both under revision, okay, which are highlighted here in the back. And so, okay, I finished, and I leave the floor to Tommaso.
Okay, so hi everyone. Thanks, Luciano, for the introduction. And now I'm going to talk about our paper that is currently under submission, as Luciano said, that is Tango, Training Free Embodied AI Agents for Open World Tasks. This is a collaboration between our DKM unit in FBK and the University of Padua. This work is motivated by the fact that we would like to have agents that are capable of solving many tasks inside the environment without actually having to learn every single task inside a specific environment. And we would also like to have an agent that is able to interact or better understanding some human instruction from natural language. To this end, what we need a set of primitives that are, as also Luciano highlighted, high-level actions executable in the environment, a way to compose these different primitives into some kind of plan automatically, in our case made with an LLM. And we also need some common sense knowledge, also this granted by an LLM. And finally, we also need a memory to remember what the agent observed inside the environment and to store knowledge, specific knowledge about the environment. Here there is an overview of our approach that is basically a neurosymbolic system for compositional embodied AI, and is composed of a set of primitives that are given to an LLM and an instruction given by an user. And this LLM should compose these different primitives in a sensed way, let's say, in order to solve the task effectively by reusing the already provided primitives inside the environment from an agent. We collected several primitives inside our framework, especially computer vision ones, like object detection, classification, visual question answering, that allow the agent to extract information from the environment. We have as well other more general primitives, like a way to evaluate logical variables, a way to terminate the current episode, and a way to understand if the current target for the agent is found. And most importantly, we have embodied AI primitives. So primitives that allow the agent to operate inside the environment and to remember what it saw about the environment. And especially our point-goal navigation model that allow the agent to move inside the environment towards a specific point. And we have a memory mechanism that in our implementation is simply a map of the environment. Then we use the LLM as a planner. How do we use it? Basically, we provide our agent with some in-context examples that are general examples, not specific for the current task, that explain to the agent how to compose the primitives for specific tasks. Then the LLM takes also the current user prompt and outputs a composed plan of the primitives that we provided to the agent. And this plan is executed inside the environment through the actuators of the agent. Our memory mechanism is based on a state-of-the-art method for navigation and especially for mapping, that is VLFM, Vision and Language Frontier Maps. And it stores a couple of maps that are an obstacle map along with the frontier of the explored area of the environment, and a similarity map. The similarity map is computed through a vision and language model called BLIP2 that extracts in a shared embedding space the embedding for the textual prompt, for example, find a bed, and the visual features collected inside the environment. In this way, the agent has the opportunity to query the map with every possible objects, and it is not limited by a pre-computed set of different objects. We tested our approach on two popular benchmarks and challenging benchmarks for the embodied AI that are open embodied question answering, where basically the agent has to answer specific questions about the environment by navigating into it. For example, who is depicted inside the photograph on top of the desk, and the answer could be Albert Einstein or whatsoever. And in this benchmark, we obtain competitive results with other methods built on purpose for this task. So it was something interesting because our approach is totally zero shot and not built on purpose for this open embodied question answering. Another interesting benchmark that we tackled is go to anything benchmark, and is a benchmark for lifelong navigation. So where the agent has not only to find one object inside the environment, but many different objects in sequence. So it has to remember what it saw in the past. And in this case, we have goals that can be multimodal. It can be a specific object, for example, a printer. It can be an image of the object, for example, a photo of an oven, or even a description of an object, for example, the printer on top of a desk in the living room. And in this case, we obtain state-of-the-art results in terms of success. So our model is zero shot and capable of finding more occurrences and more objects inside the environment, and has comparable performance in terms of the optimality of the path. Here there is a qualitative example that explains how our memory mechanism is useful for tackling this GOAT benchmark, because initially the agent has to find the refrigerator, it explores the environment, it collects the value map for the refrigerator, and then when the refrigerator is found, it automatically uses again the same map with different similarity scores for finding the description of a rug, and is capable of finding many objects in sequences without further exploration. So to conclude, our analysis showcased that our compositional approach based on LLM can effectively solve embodied AI tasks. It shows that the memory is essential to solve this kind of benchmarks. And also it shows that sometimes Tango, when the prompt given by the user is overly complicated, it can hallucinate and produce slightly wrong programs. And so there is still work to do to make it perfect. And future other work could explore, for example, the dynamic update of the plan, for example, when the plan is not exactly executable in the environment. It can, for example, consider some manipulation tasks where the agent has to manipulate different objects inside the environment, or even sim-to-real transfer, where we would like to also test our approach on a real robot. And now I'll give the floor to Leonardo.
Okay, hi everyone, I'm Leonardo, postdoctoral researcher of the DKM unit, and I'm presenting a joint work with Alessandro Saffiotti from the University of Orebro and Luciano and Paolo. This work is about learning from scratch models of the environment, in particular partially observable environments, which are stochastic in the sense that action effects are non-deterministic. So the three main contributions of this work are the definition of what is an object-centric model of an environment, and here we are considering partially observable Markov decision processes, so our model builds upon this definition. And the design of an algorithm for actually learning this model online, and also an experimental comparison with model-free reinforcement learning baselines. So what is an object-centric partially observable model? Here you can see in this example, we have the robot that can move left and right and rotate a picture in front of him. So if you think of action effects, non-deterministic action effects, here, for example, when the robot moves right, with some probability, it doesn't move. So the action can fail, the execution can fail. So the action effects are non-deterministic, or probabilistic in this case. And the environment is partially observable because the robot only perceives the image of the digit in front of it. So it cannot derive the full state of the environment from just the single image. So this is why the environment is partially observable. In particular, in this object-centric model, the states are relational since they are described at a symbolic level with objects and properties over these objects and their relations. But here we focus just on object properties. And most importantly, the observation function is object-centric. So we have, on the one hand, that the belief state factorizes in this way, where we assume that each object belief state is independent from the belief states of the other objects, which is a strong assumption, of course. But on the other hand, it allows to scale the representation of the state linearly with respect to the number of objects rather than exponentially. But most importantly, the observations are object-centric. So we assume that observations are about objects. Like in this example, we have the 9-digit, so the image of the digit. And the observation function, we assume it factorizes in this way. So here there is this example of where we define the probability of an observation of an image, given the state of the agent, the relational state, the full state, which is defined as the probability of the observation just given the state of the object which is observed. So we don't need to take into account all the state of the agent, all the state of the object, but just the object state that we are observing. And also the probability of observing an object given the state of the agent. So here with state of the agent, you can imagine the position of the agent. If the agent is at the most left position, it observes the first object, the 9. So the probability of observing the 9 is high in that agent state. And here is an example of how we can learn this model. So here we assume that we don't know the object, the predicate, the transition function, the observation function. We just know a set of actions, and we are able to perceive objects in the environment. So the first thing that the agent can do is executing action and collecting observations of the environment. So it can generate an history of observation and actions, like in this example. After generating the history, we need to initialize the state of the agent. So here we have that given the initial observation, the agent say, as an agent, I must be in some state, which we identify with that predicate P0, which is a zero-ary predicate. And the observation must be about an object, so there must be an object. So it creates this constant C0, which it identifies an object. And the object must be in some state. So it creates this unary predicate Q0, and the object is in state Q0 of C0. So that's true, and that's the object state at the beginning. But also it has to initialize the observation function. So, for example, in the initial situation, the probability of observing what the agent is observing, given the state that it has just built, is 1, because there is only one state and one observation. It cannot be otherwise. Of course, this is a very simple example. And then, after initializing the state, the agent executes an action and observes something new. And here we differentiate between the execution of zero reactions and unary reactions. So for the zero reactions, we assume that they cannot change the state of the object. So if I execute an action like moving right that doesn't involve an object, I cannot change the state of the object, of course. So for updating the state after executing the action and collecting a new observation, which is different from the previous one, and which is new in the sense that is not part of the observation function of the agent, not yet, at least. The first thing that the agent does is creating a new state for itself. So it creates this new propositional variable P1, this new predicate, zero-ary predicate, which identifies the new state. And also it creates a new constant because the new observation must be about a new object because the agent moved. And since the observation is new, it assumes that the object is also new. Okay, what about of course here, once the new predicates are introduced in the new state, they are also used for extending the whole state space, so also the previous state. And for learning the transition function, since the agent executed this action, it can, and it learned that there are two states, it can use this information also for learning the transition function in this example of the move right action. But as we said before, the zero reaction do not involve the object, so in this case, the transition function is not defined on the global state, but just on the agent state. And similarly, it updated the observation function after the new observation has been collected and the new state has been built. What about the unary action? So in this case, we are changing the state of an object. So as before, we need to introduce some predicate which describes the new state of the object. In this example, is the Q1 predicate. And so in this situation, the agent state doesn't change. So we have P1 in both states, which is true in both states, which identifies the agent state. But Q1 of C1 becomes true, is introduced as a new predicate. And again, we extend the whole state space with these new predicates, and we update the transition function for the unary object and the observation function. Okay, so there is a lot of theory behind this. We are not looking at the theory now, but this is a more general and principal approach than what we have just explained in this simple example. And we did some experiments in this domain where we only add this flip action with respect to the previous example. So the agent can move right, left, rotate, and flip the digits. But we also allow for identical digits in different positions, which can confuse the agent because it is not always able to distinguish between them. And we evaluate these for 20 different environments where the task of the agent is, after learning the model, performing some task like rotating some digits or flipping some digits. And we evaluate this with a standard evaluation metric typically adopted in embodied AI, which are the success rate, that means the agent successfully achieved the goal, or the success weighted by path length indicates the optimality of the plan executed by the agent, or the distance to success when the agent phase indicates how far the agent is from the goal. And we compare this with some model-free reinforcement learning baseline and obtain better results in more complex environments. I think I don't have time to go into the details of this figure. So what we would like to do now is extending this learning of an object-centric model to take into account also the relations between the objects, or to consider, because if you have, for example, 4 states, you can introduce 4 different predicates for representing them, or you can use 2 predicates, Boolean predicates. So we would like also to minimize this set of predicates that you use to simplify also the state space, and investigate more effective strategies for exploring the environment, like using a reward function for this, and interleaving this planning and learning in a continuous way. So here we learn the model and then we plan for solving the task. What if we keep learning while we try to solve the task, and maybe a task that is also new, so we need to learn in order to solve it. Okay, so that's the end of the presentation.
So thanks a lot to all the speakers. Questions? Anyone? Yes, on the 3 parts, yeah. The slot is unique.
I think I have a question for Tommaso. Thanks. For Tommaso, but probably it applies to everybody. So you mentioned language models kind of as planners, so not really, but somehow, no? And in the last slide, you mentioned the limitations, of course. So you said that if the task is, I don't know if you said complicated or overly complex task, no? Because can you expand a little bit on that? So what is a too complex task, and how do you think these kind of limitations can be faced? So you think that with more complicated language models, we will be able to come closer and closer to reasoning, or still there will be a need to for an actual reasoner in this kind of software in order to solve very complicated tasks? Thank you.
Okay, I try to explain better what I meant by this, and especially our main. Let me think of one second. Okay, our main issue is that basically our program generation is static at the beginning of the episode. Okay, so arrives a task for the agent for the moment, and the LLM produces a plan for this specific task. In this case, for example, it has to find a mirror inside the bathroom, so it decomposes the plan into find the bathroom, then find the mirror, then find, I don't know, the lights above the mirror, and so on. So having a static program is not completely ideal for us, because, I mean, if you fail one of the 3, for example, you fail everything. So one possible solution, except for more complicated reasoners for the moment, is, for example, introducing a dynamic update of the plan across the environment. So, for example, the LLM receives a feedback like, I found a bathroom, but there is no mirror, so the plan should be updated on find another bathroom or find something else. So this is one of the main limitations of the approach for the moment. Another solution, of course, is having more complex reasoners behind that are more capable also of overcoming this limitation from the beginning. So, for example, if you don't find a bathroom like this, maybe find immediately another bathroom. So search immediately for another one. So both the possibility, having a dynamic feedback or having a more sophisticated reasoner, could help in overcoming this limitation for sure.
Okay, thank you very much.
You're welcome.
Other questions? Anyone? There you go.
Okay, thank you. You've mentioned in the next step, so future exploration, the sim to real transfer. You see the last one?
Yes.
And I was wondering, what are the main challenges? So I think about maybe in the simulation, you train the model, or the model is exposed to 2-dimensional video, but then in reality, basically, the model is in 3-dimensional environment. So I was wondering what are the main challenges in this kind of transfer?
Okay, actually, in reality, we start also in simulation from point clouds. The main point is that we use RGBD cameras to capture the current state of the agent. So we capture an image, yes. And our biggest limitation in the sim to real transfer, honestly, is the noisy odometry, especially because, for example, in simulation, you can exploit, let's say, ground truth odometry coming in input. So you are able to effectively map without any error the environment. And one of the major limitations to overcome is exactly this. So we need a way to have a stable enough odometry to produce a coherent map of the environment without destroying everything if there is a slightly deviation in the odometry of the agent. And this, for the moment, is the biggest limitation that we are finding, because we are working on a Locobot, actually, that is a robot with an RGBD camera, that exactly as in simulation is capable of capturing 2D images after every action inside the environment. So we are already bringing the 3D world onto 2D. Also, if we have the depth image, that can be like a 2.5D, let's say, image of the environment.
Other questions? I do have one for Leonardo, actually. So if you compare your approach with standard reinforcement learning, I think that since you are generating symbols, right, it should be more interpretable. But my question is it really interpretable? So can you make sense of the symbols that you are introducing in your experience?
For some of them, I would say yes, because of the observation function. So you have that these symbols are used for representing a state, and on the one hand. On the other hand, you have this probability of an observation given a state. So if you have this P0, P1, Q0, and so on state, and you sample an observation according to this probability distribution that you learned, you can make sense out of these symbols. So in this case, I would say you can interpret in some way these through images, for example. So, I mean, if I use a symbol different from yours for describing the same image, we can understand each other. And this is also used when, for example, we set the goal, because we don't know how to set a particular goal in terms of these symbols. So we just give the images to the agent, and then the agent maps these images into symbols.
Thank you. While the others, the next speaker is going to prepare, any final question, curiosities? Well, being a planning guy, I wanted to ask Tommaso about planning via LLM, which is like a very hot topic. So why planning via LLM instead of using a standard planner?
So there is not real motivation behind this. It was because we started from the existing literature in computer vision, where they found that for composing different primitives, it is super effective and completely zero shot. It allows you to do it completely zero shot also by using an LLM. So one reason is this: we started from the previous literature and we updated it on our embodied AI setup. So this is our main motivation for the moment, but there are no real motivation behind. So also a planner probably could be used. Luciano want to add something?
I would like to complement this. The motivation is that we have the primitives. We have the primitive, but we don't have a model of what these primitives do. So we don't have a model. I mean, we know that the primitive go-to point, but we don't have formal description. We don't have a formal description of the precondition and effects. We just have the name. And the intuitive description in natural language of what this action is doing. So this prevents us in using like a formal planner. We use the large language model, because the large language model understands the natural language description of what they do.
Thank you. And let's thank the speakers again. So the next speaker is Alessandro Cimatti, and he's going to talk about automated reasoning at work.
Yeah, thank you very much. So this is basically joint work with Roberto Sebastiani, who co-leads the work package in Integrative AI for verification, synthesis, and autonomy. So the work package is basically structured in 3 tasks. One is automated reasoning, enumeration, and counting, and optimization. The second one is formal verification, planning, and synthesis. And the third one is reasoning and verification and synthesis for autonomy. So this is going to be an overview talk. I'm not going to concentrate on KPIs or publications or stuff like that. I'm going to focus on AI in the form of symbolic, logic-based, rule-based reasoning primarily. And let me state clearly that AI is not limited to data-driven techniques. And then we can discuss. Also, we are going to interpret integration as the integration of discrete and mathematical reasoning. So the idea is to proceed from the bottom up. We're going to talk about first the combinational reasoning techniques, so basically satisfiability and enumeration of formulas. Then reasoning about symbolic transition systems, that is how interpretations evolve over time, and then their application to the complex, the analysis of complex systems. Okay. So, combinational reasoning. So we start from the very basic problem of SAT, that is finding a satisfying interpretation for a Boolean formula. That is, in the truth table of a Boolean formula, what is if there is a line that evaluates to true. And its generalization is satisfiability modulo theory, where we look for satisfying interpretations of first-order formulas with respect to a background theory. So we no longer have only Boolean reasoning, but we also have individual variables, function symbols, predicate symbols, and so on. And some of these are interpreted just like we would interpret them. So like plus, multiplication, and so on really have the meaning of plus, multiplication, and so on. And these two have been very active research areas in the last probably 40 years with lots of really good results and impressive improvements. What we are going to focus here on, and what Roberto and his team have been primarily focusing on, is the enumeration of all satisfying assignment. Not only finding whether one exists, but producing all of them. And there are many variants of this problem, the all SAT, but also finding disjoint assignments, finding assignments only pertaining to certain variables, and so on. This holds both for SAT and SMT, and it is related to the problem of model countings, has applications in the abstract computation and weighted model counting. And so there have been various contributions in this area, in particular in the efficient enumeration of disjoint models for CNF formulas without blocking clauses, weighted model integration and probabilistic inference using OSMT, effectiveness of the various CNF conversions for enumeration, decision diagrams for knowledge compilation modulo theory, and so on. And what is interesting here is that these works have been addressing some inefficiencies in model enumerations, in particular because some of the techniques have not been designed for model enumerations, and therefore, like CNF transformations, were not particularly effective. Or also the fact that they typically introduce blocking clauses that tend to blow up memory. So there has been a lot of along these lines, they obtained several interesting results, and they developed several open source tools that have been publicly released. Now, I'm going to concentrate on the actual bottom line of the story that is depicted in scatter plots. For those of you who do not know what a scatter plot is, basically it's a way to compare two different solvers. One point basically says how each solver performs, and on the x-axis and on the y-axis you have the values corresponding to the two solvers. So intuitively, if your solver is if you have a scatter plot like this one, which is in log scale, by the way, it means that your solver is beating the crap out of the competitors, okay? And that's what is happening here. This holds for all SAT and also for projected also. So basically what is happening is that the model enumerator, the model enumerators developed by Roberto and team are able to produce an enumeration, a complete enumeration in much less time than the different competitors that are. Each of these plots represent the comparison with one specific competitor. For example, notice here that these are all timeouts for the competitor solver. Okay, and similarly for weighted model integration, you can see in other plots that the solvers developed by Roberto's team is able to solve way more benchmarks in way less time. Okay, and this is what is interesting is that this is not a matter of implementation; it's a matter of algorithmics, because this advantage also holds on the right because of in terms of number of integration. So in weighted model counting, the integration is the basic operation that is to be carried out. And what happens here is that thanks to the enumeration of disjoint and partial assignments, the enumerator can reduce the number of integrations that are carried out, hence resulting in dramatic speed-ups. There are also a bunch of very deep technical insights that I suggest you address Roberto about. Okay, so having this set of core engines at our disposal, what's the upper layer? The upper layer is reasoning about symbolic transition systems. So intuitively, what we wanted to do is whether a formal model of a reactive system in form of a transition system, for example, is satisfies its formal specification. Okay, and the model is basically a transition system. You can think of it in very simple terms as a state machine like this one. Okay, but the important point is that it exhibits infinite behavior over time. So it's not something that starts and at some point ends the computation. It will keep going forever. Okay? So this forces us to deal with infinite evolutions of the state over time. So the model of the idea is to represent such systems in form of by way of logical formulas, where the states are values of assignments to the variables, and we have a representation for the initial states and a transition relation, just like we have in planning in some sense. And the specification, that is what the system should exhibit as behavior, is done in form of temporal logics. For example, it is possible to formally state that a certain request is, it is always the case, this G is always the case, that a certain request is followed in the future by a response. Okay? And so the problem is, basically, how do we analyze such systems effectively? And historically, the verification landscape has been starting from the finite state model checking that we're using binary decision diagrams, has gone through a couple of major changes. One was to adopt SAT-based engines, which gave us a different set of algorithms for verification, like bounded model checking and its successors. And then there has been an evolution of SAT solvers into SNT solvers. So instead of having only Boolean variables, we have more expressive variables like real valued variables and others that allow us to represent in the very same way that we have here also more more complex and possibly infinite state systems. So in some sense, we are now working at this level, okay? And the way in which we work at this level is basically to build upon satisfiability modular theory solvers that the verification algorithms. In particular, what we gain from SMT is that we are able to represent with really in integer variables, timing aspects, resources, continuous evolution of variables, and so on, and also complex data types like lists and quantification over them. Now, the other important point is that we can represent the relationship between a concrete space that we want to analyze and its abstractions, okay? And the use of satisfiability modular theory as a core engine allowed us to increase in automation and scalability and implement and devise a number of algorithms that are a mixture of search-based, deductive, and abstraction techniques implemented in various verification tools. And also, there is a format that extends satisfiability modular theory to the notion of verification modular theory for model checking. Now, this is the set of core algorithms. And now, and there is also a lot of intricacies underneath here. We also have plots to show that certain algorithms are much better than others. But I would like to focus on how we put these algorithms at work. And so let's start off from the design cycle of complex systems. Typically, we know that a system goes through a bunch of, when it's designed, it goes through a bunch of different phases, right? We have requirements, architecture, components design, safety analysis, and so on, before we get to the implementation. And of course, we would like to satisfy, to be sure that our system satisfies functional correctness so that it does satisfy the requirements, but we are also interested in understanding if the requirements are flawed, for example. Okay, so if we put the right requirements at the beginning of the, if we put a bug at a flaw in the requirements, then we are likely to implement this bug in this flaw in the systems and realize it very late. Another very important point is how do we assess that the system is able to deal with faults? Okay, so this is something that is important for the design of complex systems, and based on this process, the engines that I showed in the previous section are being applied to in particular ways. In particular, we are going to see that they are applied in a way that tries to follow the development process, and also for model-based safety assessment, so to understand whether the faults are indeed met or not. And of course, this happens at different levels of the requirements, design, source code, and system execution phases. So let's start off with contract-based design. Contract-based design is a set of deductive techniques that tries to show that the components, that a certain system has been properly developed, in particular by attaching contracts to each the components of the system. And the idea is that these green things here describe what the components should do under the assumption that its environment will implement, will respect certain properties. And this contract-based approach can be used to carry out early validation of the refinement steps to ensure that the component reuse is correct, and also to verify the composition. Very often we hear that a certain system is buggy even though it is composed of correct components because it's the composition that makes the bugs, okay? So this is the idea here is that by specifying properly the interfaces and checking that this composition is done properly, we can ensure that the system will be correct by construction. These techniques have been integrated within an integrated design environment for automotive software and have been experimented, for example, to formally verify the correctness of autonomous functions for automated driving. Another important point is the ability to analyze complex systems under fault. Okay, so given a certain model of the system, they could come like from a Simulink specification. We wanted to understand what are the possible configurations that will bring the system to a bad state, will cause a so-called feared event. And these elements here are so-called fault trees that describe all the possible ways in which the system could fail. Okay, these are artifacts that need to be used for the system certification. So they are very important and they are very hard to construct by hand. Okay, so what we do with model-based safety assessment is to make sure that these artifacts are constructed automatically. And it was interesting to see how certain, for specific problems called the preliminary safety assessment, the adoption of a specific encodings and the use of SMT solving instead of model checking was extremely effective. So in this case, you have to interpret the plot as if they are twisted, but better. But our tool is winning because it's above the diagonal, and this is even more evident when the systems become more complex. Okay, so again, these are log scale plots, and we see that the SMT-based encoding for the generation of cut sets is dramatically better than the one based on a sequential approach. We have been applying formal verification to the reverse engineering of software. In particular, the analysis, in practice, to the analysis of legacy heat pump control software, with where we discovered the several unexpected and missing transition, and also the use of formal techniques is at the core of a large activity that we carry out in the railway domain, where the current situation is that the stations, the Italian stations, are controlled by interlocking by electrical circuits on the left here, and we are working to develop a software-based control system. Okay, so there are many difficulties here. You realize that this is really highly critical. We're talking about 1,500 stations in all Italy, and one of the first activities is to provide formal techniques to specify the interlocking procedures and to automatically generate code. Once we have this, the problem is, how do you verify them? And in particular, how do you verify them at the parameterized level? Because we have one single software that will control all the stations. Okay, so you're not verifying one single design. We are verifying a design that works for all the stations. And at the core, we have an automated generation of the conjectures and the contracts that are then solved with the SMT at the core of the engine. the other important aspect is how do we deal with the legacy systems. That is, these are systems that are literally the printout of what is happening, and there is nothing digital left. Okay? So the problem is, how do we make sure that these things can be reasoned about and confronted with the new technologies? And so the approach here is to turn these schematics into their counterpart. And interestingly, what we need in terms of expressiveness is the ability to deal with electrical circuits. So we're talking about things that can be modeled as the combination of Boolean variables and the Kirchhoff laws. Okay, so it's really arithmetic describing how the currents and voltages evolve over time. So what we have is a way to compile these things into models for the model checker and to analyze something that right now is only in the heads of the experts. They look paper and pencil to see what happens if you turn a lever or close a switch. And this is the kind of things that can be produced. This is basically the verification of what are the interactions between the possible routes in a station. Okay? So it basically tells us whether two routes can be activated or not at the same time. And this is all automatic. So at the core of this, we have satisfiability modulo theory and verification modulo theory at its power. And there are other things I would like to say, but I think Andrea is giving me the look, so I will go to the conclusions. Come to talk to me if you want to know more. So the point is, we have strong contributions at the scientific level on automated deduction and formal verification. There is a strong value in integrating different forms of reasoning, and this reasoning can be deployed in practical applications. And I think that in addition to reiterating that AI is not only data-driven, I wanted to say that there is a lot of value in integrating symbolic reasoning, in particular background knowledge, for data-driven applications. And with this, I will conclude. Thank you.
Thanks a lot, Alessandro. Questions? There you go.
So thanks, Alessandro, for the presentation. So you don't do anything with LLMs, right?
So the things that I would like to do, nobody wants to do. I would love if somebody would come here and say, you know what, I would like to help you with LLMs to automatically generate, to automatically interpret what these, let me go here. Yeah, you see here, we have a bunch of textual diagrams and also, regulations and a lot of domain knowledge, or even the relay circuits descriptions. And building the models is really a pain. Okay? In fact, we have a PhD student working exactly on, where is it? Eventually I will find my way with this pointer. Yeah. So, you see here, you have here the picture of, yes, maybe. Okay, so we have these printouts of the diagrams. And we are currently bound to doing the modeling by hand. So looking at the picture and coming up with the corresponding internal representation. Okay, so to me, this is really the work for AI. And Stefano Frizza has been working on this in basically trying to apply vision techniques to extract and detect the components, their connections, the identifiers, and so on. That would be really an interesting topic to keep working on. But also, as I said, not a chance. Okay. This part over here, the understanding how the regulations interfere with each other, or generating an operational view of the procedures that are encoded in the regulations. That would also be very, very interesting. Yeah. So if anybody wants to join forces, we are more than happy.
Thank you. Other questions?
Thank you for the talk. What about using machine learning for speeding up the search in the search space? Because this has been used in different settings, also in logic. So like learning heuristics to speed up the search.
Yeah, that's a very good point. It's been applied in the past in SMT. For example, some people in the Holger Roos in particular with the programming by optimization, they basically try to specialize the solver to the specific class of problems, right? So right now we have typically generic SMT solvers, but maybe you have a particular class of programs coming from, say, circuits or Boolean circuits, word level, then they can specialize, and they reported speed ups up to 500 times. So it's definitely a very interesting idea. So in some sense, it's the counterpart of, can I say it, of Andrea's ERC, right? So you have a generic solver, you train it to solve a specific kind of problems that you face over and over and over. Yeah, it's a very great direction, I think.
Thanks. Other questions? I do have one, but it's probably more for Roberto than for you, Alessandro.
Please.
So I was very impressed by the plot about the number of integrations that you get, right? You managed to have...
I'm trying to get there. I will never make it. Okay, you go ahead.
Okay, so, and the question is it something that comes from the structure of your benchmarks, or is it something that you can do like in general, for random instances, for example?
No, this is just exactly exploiting the structure of. Okay, I should explain what VMI is. VMI is substantially compute an integral. So you have some domain which is represented by a formula. So this very complex represents a very complex event. You have a very complex function. Typically a combination of polynomial operation and if-then-else's with linear constraints. And you want to compute the integral of this function over this very complicated domain. And this has important application mostly in probabilistic reasoning, okay? To describe if you see the function as a probability distribution and a non-normalized probability distribution and the domain as a complex event, you can find a probability and conditional probability out of that. Okay, so the idea is that since these functions have lots of if-then-else's inside, okay, the problem is that to exploit this function, so the previous version where we produced, we're not able to exploit this function, and then we find out some good tricks to let the enumeration be driven by the if-then-else structure of this formula, and this I don't explain the detail, but this really brought a larger speed up.
Thanks a lot.
If I can complement what Roberto said, these are randomly generated formulas, but we also have experiments on very fine machine learning models, and I mean the improvements still apply. Yeah.
Thanks. Other questions? If not, I think we can thank our speakers again. Thank you. And I think it's now time for lunch, right?